Hello friends, today in the unit of heat and mass transfer, we will be discussing the fundamentals of heat transfer. The most common processes found in food processing plant involves heating and cooling of foods. Common unit operations such as refrigeration, freezing, thawing, thermal sterilization, drying, frying and evaporation are carried to achieve these two tasks. In this module of how heat transfer fundamentals are related to the design and operation food processing equipment is covered. Contents. First one, systems of heating and cooling food products. Under this, we will be studying plate heat exchanger, tubular heat exchanger. Second one, thermal properties of food. Under this, we will be studying specific heat, thermal conductivity and thermal diffusivity. In the third subtopic, we will be studying modes of heat transfer. Under this, convective heat transfer, conductive heat transfer, and finally radiation heat transfer. The first subtopic, systems for heating and cooling food products. In a food processing plant, heating and cooling of foods is conducted in equipment called heat exchangers. As shown in the figure, heat exchangers can be broadly classified into non-contact and contact types. Under the contact types, we have steam inclusion and steam injection. Under non-contact type, we have scraped surface, shell and tube, tubular and plate. First one, plate heat exchanger. The plate heat exchanger, invented more than 70 years ago, has found wide application in dairy and food beverage industry. A schematic of a plate heat exchanger is shown in the figure. This heat exchanger consists of a series of parallel, closely spaced stainless steel plates pressed in a frame. Gaskets made of natural or synthetic rubber seal the plate edges and the ports to prevent intermixing of liquids. These gaskets help to direct the heating or cooling and the product streams into the respective alternate gaps. The direction of the product stream versus the heating or cooling stream can be either parallel flow, that is in the same direction, or counter flow, that is in the opposite direction to each other. Plate heat exchangers are suitable for low viscosity liquid fluids. Low viscosity here means less than 5 Pascal second. If suspended solids are present, the equivalent diameter of the particulates should be less than 0.3 centimeter. Larger particulates can bridge across the plate contact points and burn on in the heating section. In the figure, the patterns pressed on plates used on plate heat exchanger are provided. In industrial size plate heat exchangers, product flow rates from 5000 to 20,000 kg per hour often are obtained. When using plate heat exchangers, care should be taken to minimize the deposition of solid food materials such as milk proteins on the surface of the plates. This deposition, also called fouling, will decrease the heat transfer rate from the heating medium to the product. In addition, the pressure drop will increase over a period of time. Eventually, the process is stopped and plates are cleaned. Plate heat exchangers offer the following advantages. The maintenance of these heat exchangers is simple and they can be easily and quickly dismantled for product surface inspection. The plate heat exchangers have a sanitary design for food applications. Their capacity can easily be increased by adding more plates to the frame. With plate heat exchangers, we can heat or cool product to within 1 degree Celsius of the adjacent media temperature with less capital investment than other non-contact type heat exchangers. Plate heat exchangers offer opportunities for energy conservation by regeneration. These are widely used in food and dairy industries due to the cost economics. As shown in the simple schematic in the figure, a liquid is heated to pasteurization or other desired temperature in the heating section. The heated fluid then surrenders part of its heat to the incoming raw fluid in the regeneration section. The cold stream is heated to a temperature where it requires little additional energy to bring it up to the desired temperature. This figure shows a 5-stage plate pasteurizer for processing the milk. Section 1.2, Tubular Heat Exchanger. The simplest non-contact type heat exchanger is a double pipe heat exchanger consisting of pipe located concentrically inside another pipe. The two fluid streams flows in the annular space and in the inner pipe respectively. The streams may flow in the same direction, that is parallel flow, or in the opposite direction, that is a counter flow. The figure is a schematic diagram of a counter flow double pipe heat exchanger. A slight variation of a double pipe heat exchanger is a triple tube heat exchanger as shown in the figure. This type of heat exchanger product flows in the inner annular space, whereas the heating or cooling medium flows in the inner tube and the outer annular space. The innermost tube may contain specially designed obstructions to create turbulence and better heat transfer. Some specific industrial applications of triple tube heat exchangers include heating single strength orange juice from 4 to 93 degrees centigrade and then cooling to 4 degrees centigrade. Cooling cottage cheese water from 46 to 18 degrees Celsius with chilled water, and cooling ice cream mix from 12 to 0.5 degrees Celsius with ammonia. Another common type of heat exchanger used in food industry is a shell and tube heat exchanger, and it is used for applications such as heating liquid foods in evaporation systems. As shown in this figure, one of the fluid streams flows inside the tube while the other fluid stream is pumped over the tubes through the shell. By maintaining the fluid stream in the shell side to flow over the tubes rather than parallel to the tubes, we can achieve higher rates of heat transfer. Baffles located in the shell side allow the cross flow pattern. The figure shows a shell and tube heat exchanger. One or more tube passes can be accomplished depending on the design. The shell and tube heat exchangers shown in this figure are one shell pass with 2 tube passes and 2 shell passes with 4 tube passes. A wide variety of food products is processed using heat exchangers. These products present unique and often complex problems related to heat transfer. In the following sections, we will develop quantitative descriptions emphasizing thermal properties, properties such as specific heat, thermal conductivity, and thermal diffusivity. Mode of heat transfer, a mathematical description of actual mode of heat transfer such as conduction, convection, and or radiation is necessary to determine quantities such as total amount of heat transferred from heating or cooling medium to the product. Section 2, Thermal properties of foods. Under this, Section 2.1 deals with specific heat. Specific heat is the quantity of heat that is gained or lost by a unit mass of product to accomplish a unit change in temperature without a change in the state. The equation 1, which is Cp is equal to Q divided by m into delta T, gives the specific heat Cp. Here Q is heat gained or lost in kilojoule, m is mass in kilogram, delta T is the temperature change in the material in degrees Celsius, and Cp is the specific heat having the units kilojoule per kilogram per degree Celsius. Specific heat is an essential part of the thermal analysis of food processing or of the equipment used in heating or cooling of foods. With food materials, this property is a function of the various components that constitute a food, its moisture content, temperature and pressure. The specific heat of a food increases as the product moisture content increases. For a gas, the specific heat at constant pressure, that is Cp, is greater than its specific heat at constant volume Cv. In most food processing applications, we use specific heat at constant pressure, that is Cp, since pressure is generally kept constant except in high pressure processing. For processes where a change of state takes place, such as freezing or thawing, an apparent specific heat is used. Apparent specific heat incorporates the heat involved in the change of the state in addition to the sensible heat. In designing food processes and processing equipment, we need numerical values for the specific heat of the food and the materials to be used. Published information or can be calculated using predictive equations. The predictive equations are empirical expressions obtained by fitting experimental data into mathematical models. Typically, these mathematical models are based on one or more constituents of the food. Since water is a major component of many foods, a number of models are expressed as a function of water content. One of the earliest models to calculate specific heat was proposed by Siebel in the year 1892, and the equation is Cp is equal to 0.837 plus 3.349 xW. Here xW is the water content expressed as a fraction. This model does not show the effect of temperature or other components of a food product. However, in the later years, several empirical models have been developed. Some of them include Cham 1978, Heldman and Singh 1981. Choi and Wokus in the year 1986 presented a comprehensive model to predict specific heat based on composition and temperature. Their model is as follows. Cp is equal to sigma, that is summation from I equal to 1 to n, product of Cpi into xi. Here xi is a fraction of the ith component, n is the total number of components in a food, and Cpi is the specific heat of the ith component. The section 2.2, thermal conductivity. The thermal conductivity of a food is an important property used in calculations involving rate of heat transfer. In quantitative terms, this property gives the amount of heat that will be conducted per unit time through a unit thickness of the material if a unit temperature gradient exists across that thickness. In SI units, thermal conductivity is K is equal to joule per second per meter per degree Celsius or watt per meter per degree Celsius. Note that watt per meter per degree Celsius is same as watt per meter per Kelvin. Most high moisture foods have thermal conductivity values closer to that of water, that is 0.597 at 20 degrees Celsius. On the other hand, the thermal conductivity of dried porous foods is influenced by the presence of air with its low value, and the thermal conductivity of air is 0.0251 at 20 degrees Celsius. For fruits and vegetables with water content greater than 60%, the following equation has been proposed to compute the thermal conductivity. K is equal to 0.148 plus 0.493 into xW. Here the xW is same as that of specific heat, which is water content expressed as a fraction. Choi and Wokus in 1986 gave the following expression that includes the influence of product composition and temperature, and that equation is K is equal to sigma I equal to 1 to n Ki Yi, where a food material has n components. Ki is the thermal conductivity of the ith component, Yi is the volume fraction of the ith component, obtained as follows. Yi is equal to xi divided by rho I whole divided by sigma xi divided by rho I, where I is from 1 to n. Here xi is the weight fraction and rho I is the density in kilogram per meter cube of the ith component. Section 2.3 Thermal diffusivity. Thermal diffusivity is a ratio involving thermal conductivity, density and specific heat as given in the equation 11. Alpha is equal to K by rho into Cp. The units of the thermal diffusivity are alpha is equal to meter square per second. Thermal diffusivity may be calculated by substituting values of the thermal conductivity, density and specific heat in the equation 11. Choi and Okus provided the following predictive equation obtained by substituting the values of K, rho and Cp in equation 12, and it states alpha is equal to sigma alpha I xi, where I is from 1 to n. Here n is the number of components, alpha A is the thermal diffusivity of the ith component and xi is the mass fraction of each component. Section 3 Modes of heat transfer. Heat energy is simply the sensible and latent forms of internal energy. The heat content of an object such as a tomato is determined by its mass, specific heat and temperature. The equation for calculating the heat content is as follows. Q is equal to m into Cp into delta T. Here m is mass, Cp is specific heat, delta T is the temperature difference. Although determining heat content is an important calculation, the knowledge of how heat may transfer from one object to another or within an object is of even greater practical value. The three common modes of heat transfer are conduction, convection and radiation. Section 3.1 Conductive heat transfer. Conduction is a mode of heat transfer in which the transfer of energy takes place at molecular level. Note that in conductive mode, there is no physical movement of the object undergoing heat transfer. Conduction is the common mode of heat transfer in heating or cooling of opaque solid materials. Consider the heat transfer across a room wall as depicted in this figure. The rate of heat transfer through the wall may be expressed as Q is proportional to wall surface area into temperature difference divided by wall thickness. In mathematical terms, Qx is proportional to A into dt divided by dx. Here dt is the temperature difference and dx is the wall thickness. Or by inserting a constant of proportionality, the Qx becomes Qx is equal to minus k into A into dt divided by dx. Here the K is the thermal conductivity having units watt per meter per Celsius degree. A is the area normal to the direction of heat transfer, whereas T is the temperature in degrees Celsius and x is the length in meters. This equation is also called as Fourier's law for heat conduction after Joseph Fourier, a French mathematical physicist. According to the second law of thermodynamics, heat will always conduct from higher temperature to lower temperature. Section 3.2 Convective heat transfer. When a fluid, liquid or gas comes into contact with a solid body such as surface of a wall, heat exchange will occur between the solid and the fluid whenever there is a temperature difference between the two. During heating and cooling of gases and liquids, the fluid streams exchange heat with solid surfaces by convection. The magnitude of the fluid motion plays an important role in convective heat transfer. For example, if air is flowing at high velocity past a hot baked potato, the latter will cool down much faster than if the air velocity was much lower. Depending on whether the flow of the fluid is artificially induced or natural, there are two types of convective heat transfer, that is forced convection and free convection. The free convection is also called as natural convection. Forced convection involves the use of some mechanical means such as pump or a fan to induce movement of the fluid. In contrast, free convection occurs due to density differences caused by temperature gradients within the system. Consider heat transfer from a heated flat plate PQRS exposed to a flowing fluid as shown in this figure. The surface temperature of the plate is Ts and the temperature of the fluid far away from the plate surface is T infinity. Overall, we see that the rate of heat transfer from the solid surface to the flowing fluid is proportional to the surface area of the solid, that is A, in contact with the fluid, and the difference between the temperatures Ts and T infinity. Mathematically, Q is proportional to A into Ts minus T infinity, or Q is equal to H into A into Ts minus T infinity. Here, A is the area in meter square, H is the convective heat transfer coefficient, also called as surface heat transfer coefficient, expressed as watt per meter square per degree Celsius. This equation is also known as Newton's law of cooling. Note that convective heat transfer coefficient, that is H, is not a property of the solid material. However, it depends on number of properties of the fluid, the velocity of the fluid, geometry, and the roughness of the surface of the solid object in contact with the fluid. Section 3.3 Radiation heat transfer. Radiation heat transfer occurs between two surfaces by the emission and later absorption of the electromagnetic waves. In contrast to conduction and convection, radiation requires no physical medium for its propagation. It can even occur in a perfect vacuum, moving at the speed of light, as we experience everyday solar radiation. Liquids are strong absorbers of radiation. Gases are transparent to radiation, except that some gases absorb radiation of a particular wavelength. Solids are opaque to thermal radiation. Therefore, in problems involving thermal radiation with solid materials such as solid foods, our analysis is concerned primarily with the surface of the material. Thermal radiation emitted from an object surface is proportional to the absolute temperature raised to the fourth power and the surface characteristics. More specifically, the rate of heat emission from an object of a surface area A is expressed by the following equation. Q is equal to sigma into epsilon into A into Ta power 4. Here, the sigma is the Stefan Boltzmann constant, which is equal to 5.669 into 10 power minus 8 watt per meter square per Kelvin to the power 4. Ta is the absolute temperature, A is the area, epsilon is the emissivity, and this describes the extent to which a surface is similar to a black body. For a black body, the value of emissivity is equal to 1. Conclusions. In this module, we have studied fundamentals of systems for heating and cooling food products. A heat exchanger is a device used to transfer heat between one or more fluids. Plate and tubular type heat exchangers were detailed in the present module. Thermal properties of foods and beverages must be known to perform various heat transfer calculations, and these heat transfer calculations are involved in designing equipment and estimating process times for processing foods and beverages. In the present module, thermal properties such as specific heat, thermal conductivity, and thermal diffusivity were detailed. Finally, three different modes of heat transfer, convection, conduction, and radiation, has been discussed with their governing equations. Thank you.